Greetings. So there's these three masses, and from the front, let's say there's a locomotive or the head train, and it pulls it by a force of 50 newtons. There's no resistance to the motion towards the right because there is zero friction declared. Again, a very simple example. And what I want to talk about is the tension on the rope here, connecting the first one and the second one, and then the second to the third carriage. What is the tension between those wagons on those ropes? And just again, for simplification, not only is the friction zero, but the weight of the ropes is zero as well. There's no other losses on the way, which makes it all simple. And this is supposed to be straight. Alright? So, how to calculate this is basically to first realize the overall mass. The overall mass of all these three things. It's a good thing to just practice realizing, well, just add up all these three things. So MA, like mass of everything is 6 kilograms. Then, what I can realize here is that the 50 newtons is the force powering the motion and the acceleration of this entire thing. So I can even calculate straight in the beginning the acceleration of this system. Well, I can do it this way. I know these ropes cause no loss in the force, and I know that all these things accelerate together at the same rate. They all have the acceleration because they are a connected system by the ropes. Therefore, when talking about acceleration and looking for acceleration, I can just do again this basic equation for all these cases. Force equals mass times acceleration. Solve for acceleration and then use the 50 newtons, which pulls all the three, and divide it by the mass of all three together. Because they are all pulled and have the acceleration all together, they act as a single object in a way. Because now they really are connected by the ropes and they are acting in a unified fashion. That means that the acceleration is 50 over 6 or 25 over 3 meters times second to the minus 2. Alright, so it's expressed as this fraction, but it's okay. Alright, so that's the acceleration, just to take it out of the way for the beginning. And now, from that, I can imagine at what rate this entire system accelerates when 50 newtons is applied to it. When there's a set of carriages of a train or something, they together have 6 kilograms, and the 50 newton force is pulling them towards the front. There's no friction, there's nothing keeping them back. Well, there's actually quite high acceleration. Now, what I want to calculate is the tension, just like I know that logically, because from the front, all three are pulled by a friction of, and by the way, what is really interesting to realize here is one can start seeing this in a completely manner. By just looking at it through the real lenses, there's 50 newtons applied by pulling here, creating tension on this rope, right? Creating tension like this, and then the person, let's say, or the locomotive, so something that pulls it in the front, it has to pull it like this. So there's this tension on the rope, and the tension is precisely equal to the pulling force, right? So the tension on the first thing that's pulling the rest is the 50 newtons. Now, how did I know the acceleration, for example? Well, I used the mass of all three that were behind it, right? All three that were pulled by it, and used this quantity and divided the force by it. I divided the 50 newtons by it. Now, if I want to get the force back, what I can do is I can use this acceleration again, and I can look for this 50 newton force that I already knew in the beginning. It was the first out of few information pieces that I had right in the beginning, called anything. And force is m times a. But m was all the ones behind it, all the ones that it pulled. And a is something I looked for, so it is 25 over 3, and all this will be in newtons, by the way, afterwards. 25.3 times the m, so the a is the 25.3, the order of multiplication doesn't matter, and the m is the 3 together, which is 6. So again, I have the 50, right? I again have the 50 newtons, which is right. Now, the same thing will apply when I'm looking for tension on this rope, for example. So again, there's this tension that this thing does in this direction, that it actually holds on the rope, and the rope has the tension inside itself, because the pulling force of this one is translated to the rest by the tension on the ropes, and this one extends the force on the one behind it by holding it behind itself in a way, right? So the tension force here, let's say tension force 2, will be, because this is the first one, the pulling one is actually tension force on the rope of the pulling device and in front of all the carriages. Now, behind the first carriage and in front of the second and third carriages, there's a tension between these two, right? Behind the first one and the second one. And how is it determined? It's again the same idea. I have to use m times a, it's the same thing. The a is still the same because this entire system still has the same acceleration. If all these things together are accelerating at the same, they're at the same speed, they're accelerating at the same rate, and that is the 25/3 meters per second squared. But I won't even write the unit right now. And then it's multiplied by the mass. But the difference here is, here I was counting with all the mass behind it, so it was 1 plus 2 plus 3. But here the only mass left, still pulled by this rope from this one towards here, is just the mass of those that are still behind it. So it's just the 2.3, it's only the 5. So now it's going to be 125/3 newtons. That's the tension force between the first one and the second one. Because the second one behind itself further has the mass of 3. So it's always, the tension is the one that I know that there's some acceleration for the entire system, especially when it's all accelerating together at the same rate. So that's really easy thing that keeps a lot of questions out of the way. And I just have to multiply by some mass. But I know that to get the tension on the rope, well, I use the mass that the rope further pulls behind itself. And in this case, it's only the leftover 5 kilograms. Here, for FT3, let's say, again, it's m times a. But the m will be yet again different because a is still the same. The acceleration for the entire system, all these three things together, or this formula that wasn't in the experiment in the first part of the time I'm talking about this, the common acceleration of all this together is 25.3 meters per second squared. And again, it has to get multiplied by some mass, and the mass it gets multiplied by is what it further pulls behind itself. But the only thing left is the last carriage in this one. The tension force between the second one and the third one, the last one, is just the remaining mass of the ones still pulled behind it, and it's just this 3 kilograms. So the tension force between this one and this one is again the same acceleration, but just times the mass that is still left behind it, that it still pulls behind itself. Because this rope pulls this one, but it also pulls this one. But this rope, it only pulls this one. It doesn't pull this one and this one and this one. That's why the tension was the highest in the front. It had to pull this one and this one. The tension here is lower because it doesn't have to pull this one. It's just pulling these two behind this one. And then the tension is the lowest, namely 25 newtons. And this one, because it's the same acceleration, but multiplied just by the one it really pulls, and it's this one that it is holding.